All right, I'm gonna do a little bit of a different video because I don't have a printed copy of this to show you. I don't have a printed copy of your quiz to do a key for, but I wanted to be able to use my modeling kit to answer some questions. So I'm going to do an iPad key with my modeling kit. So we'll see how this goes. So first I'm gonna say the first question, we're just naming the molecule. So naming the molecule, we have 1, 2, 3, 4 for our parent chain. That's the longest chain I see. Sometimes I like to check, there's another methyl over here, but that's also just 4. So the best way to number it seems like would just be straight across 4 to get our parent chain of butane. And if our parent chain is butane, then we have to decide how to number it. So there's a few different ways we could number it. So I like to number in different colors. So we could start here, 1, 2, 3, 4, or we could go the other way, 1, 2, 3, 4. In theory, we could also start here, make this 4, or make this 1. But because these methyls both connect, either it goes 1, 2, 3, 4 or 1, 2, 3, 4, it actually that doesn't make too much of a difference. So this molecule would be butane. And then we find our substituents. So here's one substituent. Um, and here's another substituent and a third substituent. And what I like to do, I guess the first step we do is step one, name the parent chain, which we already did. And then step 2, identify and number. Number the substituents. So identifying and numbering the substituents. So 2 fluoro, 2 methyl, and then 3 chloro if we go with the green numbering system. If we go with the maroon numbering system, these would be 2 chloro, 3 fluoro, 3 methyl. Okay, so between those two, the green one has the lower number, so I would go with that. For step 3, combine them all. So let's see. I was about to redraw it for some reason. So that would be in alphabetical order. They have to be in alphabetical order to be correct. Alphabetical order. So that would be chloro comes first. So 3 chloro, then fluoro for A, B, C, D, E, F, 2 fluoro, 2 methyl. I'm running out of space, but butane would be the last part here. Okay, so that is the right name, except that you have to consider nomenclature, or sorry, you have to consider stereochemistry. So that's kind of a step 4 is step 4, check for stereochem. And we don't have a double bond, so we can't do cis or trans nomenclature here, but we do have wedges and dashes given, so there's a potential that we would have to identify a chiral center. So if we're looking for our chiral center, this carbon has 2 methyls, so that's not a chiral center. This carbon has 3 hydrogens, so that's not a chiral center. This carbon has a methyl, an ethyl with other things off of it, a chloro, and a hydrogen. So this is a chiral center, and we already have the hydrogen pointing back. So we have to consider if this is RS, this has 3 hydrogens, so it's not. So the first thing you do is you assign highest priority, and this is based on weight. So chlorine is heavier than carbon or carbon. These 2 carbons, though, they're both carbon. So between them, you would compete between second and third position. So both of these are carbons, but then you look at and see what are these carbons attached to. This carbon has a fluorine and 2 other carbons, whereas this carbon just has 3 hydrogens. So fluorine is heavier than hydrogen, so this gets position 2, and then this gets position 3. Oftentimes students don't think about all of that because they are like, oh, this whole group is heavier. And that's not the right reason. You're only looking at the first point of difference. So make sure that if you got that right, you got that right for the right reasons. The hydrogen's already pointing back, so we don't have to worry about it. And we can just connect these 1, 2, 3, and that is going clockwise. So I would say this is R. So the proper name for this is R3-chloro-2-fluoryl 2-methylbutane. So if I was grading, or when I make the key for this, what I'm technically going to be looking for, this question's worth 5 points. So did you get the parent chain? Did you get all 3 substituents with the right number? So that would be like half a point for number, half a point for substituent. And then did you get R or S configuration? Okay. The next question is the Newman projection looking from C1 to C2. So, oh, I already was working on this and then I realized that I wanted to use my model kit, so I'm going to delete this. So I did let my PLTL leaders borrow my modeling kit. So I'm having to work with one that's not as nice as what I normally work with, and I'm sorry about that, but your PLTL leaders then have a nicer one. So what we're going to do is pretend all the black and tan are carbon. So hopefully you see that this looks like the carbon chain that I have here. So this is my 1, 2, 3, 4. And then we have our fluorine in green coming out towards us. So just to make that easier to follow, I can put that fluorine in green here. And then black and tan. This one's tan. These are tan for these carbons. And then I have the purple for the chlorine here. So hopefully you can see that. Okay, I don't have any of the implied hydrogens yet or the drawn in hydrogens. This is just my carbon chain, my fluorine coming towards me and my chlorine coming towards me. Okay, so the question asks for us to look from carbon 1 to carbon 2. I had actually intended to ask 2 to 3, but I just had a typo. That actually works in your favor. Carbon 1 to carbon 2 is a little bit easier. But I will, if you did do the one from carbon 2 to carbon 3 without thinking, I'll give partial credit for that. So we have 3 implied hydrogens here. So I'm just going to draw those 3 implied hydrogens in. And then I'm going to attach them here. So that's like one step that you have to do to get this right, is you have to draw in your implied hydrogens. And I'm going to make the hydrogens silver. It's slim pickings that I have left over from my own modeling kit because I wanted the PLT leaders each to have their own set for these 2 chapters. Okay, so if we look here, I'll bring it back to the way it was before. This is from carbon 1 to carbon 2. This is my fluorine coming out of the page towards me. This is my CH3 going into the page. I've added in my hydrogens here. So the Newman projection would be looking from carbon 1 to carbon 2. So carbon 1 to carbon 2 is what we are looking at. So this is the image that we're going to see. So the first carbon you can see is represented by this shape right here. That's why we draw it like that, is because in this tetrahedral arrangement, you get this sort of like Mercedes-Benz basically symbol coming towards you. It's 3D, but we don't draw that in the Newman projection. It's assumed based on the fact that there's another thing behind it. And the reason we draw it as that circle is if I was trying to see that, it sort of looks like a circle, it just shows up as a circle behind. So, and then that circle behind this carbon has 3 things bonded to it. So we have 3 hydrogens on our front one, these 3 silver guys, and then this fluorine coming up to the right, this CH3 coming up to the left, and then down here we have our other carbon. It has a chlorine off of it, this purple thing right here, and our hydrogen here. Now, oh, sorry, that was your CH3 over here. Here's CH3. You don't have to draw in the hydrogen because it's implied. So you should be able to do this without your modeling kit. It's faster if you don't have to rebuild it every time. And the way I do it is I imagine, so when we have the model laid out nicely like this, I imagine that I've shrunk down and I'm a tiny person standing right here. and I'm looking this way. So if like, say this is me, this is my hair, this is my face, I just imagine myself standing right here, looking at the model. And if I was doing that, then what would things look like? Now, some people, like I think one of your PLTL leaders always tells me that for him, it's easier to rotate it in his mind. And so he'll just rotate the molecule. But for me, if I try to rotate the molecule, things get mixed up and out of order. It's hard for me to keep them in place. So I, in my mind, keep the model where it is and I walk around it. I imagine I'm a tiny person walking around it. So whatever works for you, you'll have to figure out. And ultimately, you'll have to figure that out for yourself and find a consistent way to get things right. Now, I had mentioned if you, without thinking, just did it from carbon 2 to carbon 3, that's totally fair. That was my typo. So I'm going to take these hydrogens off. I'm going to show you what that would have looked like as well. So now we're back to the base model with a fluorine coming towards us, methyl there, chloro here. So this chlorine has a drawn in hydrogen right here going into the page. So hopefully you can see how this looks a lot like what's drawn here. Let me zoom out a little bit. Ah, hopefully you can see that. So we've got our fluorine pointed up and out, our chlorine pointed down and out. And so if I was looking down from carbon 2 to 3, I'm going to give partial credit if you did this, since that was my mistake. Carbon 2 is in the front. So this carbon 2 is in the front and it has the fluorine still sticking up off of it. It has the CH3 on the left side and this CH3 coming down here. And then back behind it, we have this one, this other carbon with our chlorine. And our chlorine is sticking out, but kind of down. So you can see it's like got that staggered thing happening there. It would probably be better rotated like this. You can see it's staggered. It's not eclipsed on one another. So the chlorine pointed down, fluorine pointed up. And then over here we have that hydrogen that I'd put in silver. And then straight up behind, we have our methyl group, this one right here. So this, either one of these, I'll give partial credit for this one. I'll give full credit for this because that's technically what the question asked for. And it was a little bit easier to draw because you just had to do those 3 hydrogens. But you needed to make sure that you're keeping your wedges and dashes in the right place because otherwise you might change the chirality of the molecule. So yeah, that's what's going on here. Hopefully you can see that. The next one, I don't have a model for, unfortunately, but I do have several very good videos for this. One of my students told me that that video was life-changing for them, and that made me laugh. So here is a chair conformation, and we have 2 CH3s pointing in the axial position and pointing up. So the reason I know those are in the axial position is because they're going straight up. And then these alternating ones that would be going up, they'd be at an angle. So these has a hydrogen down. This one would be up. This one would be angle down. Let's see. Oh, I drew in one. So this is straight up. This one would be at an angle up. This would be straight up. This would be at an angle up. And this one would be straight up. So you can see that these 3 that are axial and pointing up, they're all in the same direction. I think in my other video I did, I made all of them have purple bonds and they're all pointing straight up. Those are the things that are going to be the most effective, or sorry, those are going to be the things that are going to be all pointing the same direction. So all those are cis to one another. So when I say this part about like prefix of cis or trans, hopefully at this point you're starting to be able to tell when things are pointed up and when they're not. And so these 2 being in the up axial position mean that they are cis. Another way you can do it, this was easy for me for a while, is I would see the CH3 is up in axial. And so then the one next to it that was pointing up would have to be equatorial. And then the one next to that that's pointing up would have to be axial. And we do have these 1, 2, 3 apart, and they're both axial, so they must both be wedges. So these are cis. Okay, but I got a little bit ahead of myself. I got excited because I don't have my modeling kit, but the first thing you would have to do is number, and I can tell that this is the longest chain present because it's a ring. And so it's 6-membered ring, 1, 2, 3, 4, 5, 6. So that means that hexane is our parent chain. So step 1, we find our parent chain, hexane, and in this case, cyclohexane is our parent chain. Step 2, we identify our number, our substituents. So 1, 2, 3, if we go this way, if we go the other way, 1, 2, 3. It looks like either way we have 1,3-dimethyl. So it doesn't matter which direction we start because there's a symmetry there, so doesn't matter. Next, we would then combine all in alphabetical. So this would be 1,3-dimethyl cyclohexane. And then the last thing I do, sort of a fourth step, I check for stereochemistry, and these are cis to one another. And I had somebody ask me, like, could you do R and S conformation on this? But because there is a plane of symmetry right through the middle, if you think of it like this, this does not have an enantiomer. This is not a chiral molecule. So cis or trans would be correct, but I tried to not make you worry about that by just saying to include cis or trans. Okay, now this last one, match the following names to their correct angle of rotation. So the names are listed down here. You could have eclipsed, not fully eclipsed. The largest groups are not covering one another. You could have eclipsed, fully eclipsed with the largest groups covering one another, staggered anti, or staggered gauche. And so I'm going to adjust this a little bit. I'm going to try to sort of draw have a Newman projection here for you that would help you see this. I think I need to probably make a Newman projection video, but I do not have my kit right now, and I might have one already. So I'll look for one and I can post it in our class group me if that will help. So I'm gonna just say this big blue group on this side is the biggest group here. And then this big blue group is the biggest group here. So, and then everything else we'll just say are hydrogens. Okay, so if I'm looking at this, these big groups, they are going to be able to repel one another pretty easily. So these two, if they're on top of each other, they have a lot of electrons. They're going to be pushing one another away. It takes a lot of energy. It's like when you push two magnets together to get these anywhere near each other. So this is high in energy. When we have our two groups eclipsed like this, so eclipsed means covering up one another. So this position that I have drawn right here, this is the eclipsed, fully eclipsed position. And our two largest groups are covering one another, and that is the highest energy. So whenever I come across one of these, I always try to find the highest energy point and the lowest energy point because I automatically know that the highest energy is going to be the two largest groups covering one another. And so that is at position 0 and 360. That 0 and 360 is fully eclipsed. Okay, and then the lowest position is when those groups are farthest away possible. So they're staggered, they're not covering one another up. None of these groups are laying on top of one another. So they're staggered. And then they're fully anti. So this position is the lowest energy position. For fully, the two groups are farthest apart. That would be we already assigned this one, staggered anti, like totally opposite. So that would be 180, staggered anti. So it doesn't really matter what this molecule is. It clearly has like some symmetry because there's not a bunch of varying in the groups here, but it's going to have a position where its two biggest groups are opposite one another and a position where its two biggest groups are on top of one another. And that is easy to identify as the top and bottom positions. Now, there are other staggered positions where these two groups are near each other, but they're not fully on top of each other, so they do have some space like between them right here. Here, let me, like this space between them. So they have a space to spread their electron density up and down. They're not hitting one another. So with that space between them, that stabilizes them quite a bit. So that would be putting them at a lower position, lower, but not lowest. That is going to be your other staggered position. So these two at 60 and 300, this is a lower energy. So this is staggered, but it wouldn't be anti, it would be gauche, which means, I think gauche technically means left, but it also can mean awkward. So like these are awkwardly close to one another in French. So what that means, so that's where I would put staggered gauche. So that's this one. So we already assigned that one, and now we're assigning staggered gauche. So you could say, okay, what's left is eclipsed, but not fully eclipsed. But I'm going to show you if we keep rotating. So our 0 degrees where we were completely covered was right here. We went 60 degrees and they were staggered gauche opposite each other right here. So a little bit better, but not great. And then if they're laying right on top of each other, but it's not the two biggest groups on top of each other, that's higher in energy, but it's not the highest. The highest is the one we started with up here. So this would be eclipsed, but not fully eclipsed. Eclipsed where not fully eclipsed largest groups are not covering one another. So, and then if we were to keep going, we would get anti where they're completely opposite each other at 180. And then we go back around and now we're back to eclipsed, but not fully eclipsed. And then we go to staggered, but they're opposite one another. So a little bit more stable, but not as stable as anti. And then the least stable position is right here at 360. So I hope that clears that up. Let me know if you have any questions on this quiz, and you'll have another quiz. I moved it next week to Friday in place of what would have been an exam that covers some of chapter 5. And then our exam we pushed back 1 week. So let me know if you have any questions. Next quiz will cover chapter 5, and I'll see y'all then.